Hello everyone, my name is Kristen and I'm a master's candidate in software engineering. I'm supervised by Alexander Essex at Western University. Today I'm going to discuss our paper Indiscreet Logs, which outlines potentially backdoored Diffie-Hellman parameters in use across TLS and STARTTLS. Diffie-Hellman key exchange should use a prime modulus, but what would happen if the modulus was not prime? That modulus could be a backdoor, since it works in a group of unknown and potentially smooth order, and no one would know except the attacker. Browsers can't detect them due to poor parameter validation, and companies we spoke to could neither confirm nor deny backdoor use. Backdoored moduli could be in use today, and no one except the attacker could tell. We found evidence of hundreds of composite moduli and millions of non-safe prime moduli in use in HTTPS, IMAP-S, POP3S, SMTP-S, and SMTP over STARTTLS. If these moduli are backdoors, the attacker could passively eavesdrop on the TLS connection and decrypt any traffic from that connection. Since Diffie-Hellman parameters are infrequently modified, these backdoors could persist across numerous connections. So how is it possible that composite moduli could exist in the wild? Many cryptography implementations have poor parameter validation that enables this to happen. All major browsers do not properly validate Diffie-Hellman parameters. Browsers do not check that P and Q are the appropriate lengths as defined by NIST. They do not check that P and Q are prime, that Q is a divisor of P-1, or that elements like the public key are even in the group. Browsers will reject connections where the parameters are in a subgroup of order 2, or where the modulus is even. However, these tests do not defend against weak parameters in small or smooth order. The implication of browsers' limited parameter validation is that browsers accept almost any parameters. We demonstrate this by serving Chrome 52 parameters that use a group of order 3, allowing for a private key of 1. Higher versions of Chrome have deprecated Diffie-Hellman cyphersuites altogether. In this demonstration, we connected to Chrome under Diffie-Hellman using a prime 2048-bit modulus and a generator G which generates a subgroup of order 3. The public key then equaled the generator, which resulted in a private key of 1 mod 3. In the previous example, we connected to Chrome under Diffie-Hellman by serving only Diffie-Hellman cyphersuites from our web server. If Diffie-Hellman is not chosen by default, which is the case in approximately 99% of TLS connections, then an attacker can man-in-the-middle a connection in TLS 1.2 or below to force Diffie-Hellman to be chosen. This man-in-the-middle attack works if the client supports Diffie-Hellman cyphersuite, which is the case in the current Firefox and Microsoft Edge versions, for Chrome 52 and below, and for Safari 8 and below. The man-in-the-middle will have already placed the weak Diffie-Hellman parameters, and so modifies the client hello to offer only Diffie-Hellman cyphersuites to the server. The attacker then uses the weak parameters to calculate the master secret and modify the finished messages. The connection proceeds with the man-in-the-middle passively eavesdropping on the connection. To place the weak parameters for use, an attacker has 3 options. The first option is to inject the weak parameters as a backdoor payload onto a server. This does not require source code modification and therefore creates a persistent backdoor. To use this attack method, an attacker must have previously acquired root access through another exploit. Although root access would allow for other attacks like stealing the server's private RSA signing key, such an attack requires active eavesdropping as opposed to passive eavesdropping. Another attack vector requires an attacker to submit the weak parameters as a patch to an open source project. The backdoor parameters would then be installed for any user of that project. SOCAT recently published a security advisory about composite modulus that outlined a similar scenario. The final attack vector requires the attacker, a company employee, to install the weak parameters onto a network appliance like a load balancer before shipment. Many companies we talked to outlined similar scenarios when explaining the location of their composite moduli. To find weak Diffie-Hellman parameters in the wild, we conducted zgrab scans for mail protocols and used census scans for HTTPS. In HTTPS, there were 11 million IPs supporting Diffie-Hellman. We found 280 IPs using composite moduli and 1.6 million IPs using non-safe prime moduli. In mail protocols, we found a total of 272 IPs using composite moduli. We completed partial factorizations on many of the moduli found. By using Cato-NFS, Polig-Hellman, and Pollard's P-1, we partially recovered up to 50% of the length of some private keys. We completed vulnerability disclosures to over 15 companies, which resulted in one company submitting a CVE. Many of the companies have fixed the vulnerability since then. However, no companies were able to confirm or deny the existence of a backdoor. To stop this vulnerability from occurring, there are a few options to consider. The first option is to deprecate Diffie-Hellman cipher suites like Chrome and Safari have done. The second option is to properly verify Diffie-Hellman parameters, which has a computational cost at runtime. Using named parameters like elliptic curve Diffie-Hellman is an option that already has a proposed RFC. Finally, signing all previously seen messages in the server key exchange would prevent cipher suite modification, although it would not prevent this vulnerability from being exploited if a Diffie-Hellman cipher suite was chosen by default. To summarize, we found moduli that could be backdoors. Companies we talked to could not confirm or deny backdoor existence, and we couldn't factor the moduli completely to find out ourselves. Even if we could completely factor these moduli, that would not be conclusive proof of a backdoor. The very presence of a backdoor is easy to deny, which makes it nearly impossible to prove one is being used. So why should the possibility of this type of backdoor be allowed? After disclosures, a CVE, and other concurrent published research, there are still at least 17 IPs using moduli we found that have unknown group order. Allowing a potential backdoor like these moduli to exist is a problem that needs to be fixed. For more information on this topic, our research paper Indiscreet Logs is published in NDSS 2017. Visit our labs group's website at whisperlab.org for contact information and more information on our research.